My first task is to introduce our guest lecturer, or lecturers for today, and those who have not been here before, that will be an opportunity. I have on my left Professor Samuel Anjila, Associate Professor from Carleton University of Ottawa, Canada. Graciously through the United States government, we got him loaned to us. He's a African Canadian. For many years he's been in Nigeria, worked in Nigeria, was in France, in Lesotho, bought to Lisbon in South Africa. Then unfortunately we couldn't hold him down. The Canadian poached him away. But through a program by the US government, they say, okay, we know we have poached a lot of your brain from Africa. Okay, we can be loaning you from time to time. Those your brain, but we have poached that, come down. So the Carnegie African Diaspora Fellowship, made provision for Africans in diaspora to visit our university to give back a bit of what they have. That is the fellowship program through which Professor Anjila has been here. Professor Anjila, I want to welcome you on the second phase of visit. He's to be with us for 3 months, but he spent about 6 weeks the previous time. He's spending 7 weeks this time around. And we're hopefully by 15th of August, I'm afraid he has to go back to base. And then we're hoping whatever he deposits here will be a permanent one. And this is the only way by which we can benefit from the program. So Professor Anjila, you're welcome. As the title says, the workshop is seminar series, Machine Learning and Deep Learning. Today the second guest lecturer, somebody very popular, is our host here actually, Professor Pius Wolawi, often known as Professor Pius, just call him Professor Pius. So let's clap for our two guest lecturers. So there will be many more that you will be driving, in advanced days. Thank you, Prof, for coming. 2 days ago, I was having a Skype meeting with our collaborator in the University of Trento in Italy, Professor Pasto Vincinglia. And what he told me is quite amazing. I told him what we are doing here. I was excited. And he said in Europe, there's so many jobs now. But because before they take you or consider you at all, they assume you have knowledge, hands-on knowledge of machine learning in the list. That is the intel now. So it's not by coincidence that we have this program at a time like this. Each time they tell me, well, I came to here, I was in Botswana for 17 years. They moved down here about 11 years ago. Each time they tell me we're training for South Africa, I said, stop that. Anybody we are training today should be for the whole world. They say we have 28% unemployment now. Why should somebody be glued to South Africa? Why do you have skills to fly to Europe and everywhere? And Pro was telling me yesterday, a diploma graduate of his is now in the US. He just did Google Digital Skill for Africa and got certified in some element of it. The guys in the US now with diploma from here. And we're not talking theory. 1981, I moved from Africa to Europe with bachelor honors degree in computing science from Nigeria. And within 6 months, they said, oh, boy, I think you are good enough. You want to go straight for your PhD. Rather finish your master's. We allow you. And to God's glory, by 84 December, I defended my PhD thesis. It's the correction that took me to 85. So that's why you see when they put my record now, yes, bachelor honors degree computer science, PhD computer science, no master's degree. So why not you in Africa? Prof's approach, it will give enough, going from the basic principle. You are not to be trained how, but why also. Why should I use this CNN and not LSTM? Why not RNA, not ordinary answers of formula? So I'm proud to do a lot of hands-on work, Professor Pius. Today, please don't miss any of the 2 sessions. It's going to be for your good. So what I'm saying is that you are in the state of the art, what the world requires now, and the whole world, we are currently developing an AI strategy for African government to adopt AI for development. Even Africa is not left out. So that took us to study what's going on in China, in America, all the world now. That's the competing realm now. And it is whoever will build the capacity of his people to do this, so there are people who can actually, link up with the new age. They call fourth industrial revolution. So I'm just saying all this to encourage you, to motivate you, that whatever it costs you to acquire this knowledge, it's really worth what it's sought. It's a picture of a little back. Thank God having Professor Ejila, Professor Pius, deliver this to us. Thank you. So please pay attention and do your best today. God be with you as a continue. Thank you, Professor Ejila. Over to you.
Thank you. Good morning. Professor Joe has already given a wonderful introduction here. We have 2 parts to the seminar series. There's the machine learning part, which I gave some introduction some few weeks back, and Professor Pius is going to go into the hands-on in terms of simulation, making use of MATLAB's Simulink. And further on, probably next week, I'll be able to introduce us to Weka 2, for those of us who have not used it before. So my part of the seminar series is based on deep learning. Today we are going to look at the foundation. Okay, I believe in anything that you want to do, there's need for us to be able to know the reason, what Professor Udo called why. Why? Where does this come from? There's no theory or principle anywhere in life that just drop down. There has to be a beginning, and there has to be a reason why that theory or principle is being used. So today what we are going to look at will be, in the first place, the basics of linear models, and we'll move on to deep feed-forward networks. Even the deep forward networks will be the foundation for what we call deep learning. And next week, on Saturday, we move on to looking at training and evaluating deep networks. It's very important when you are dealing with big data analytics and using all these machine learning techniques to be able to actually act from a knowledge of the training and how to measure the performance of your training. Okay? Then we move on to convolutional neural networks, and eventually, if we have enough time, I'm going to introduce us to Weka 2 through example, and we're going to go through the example. On August 13, we're going to look at recurrent neural networks, and a typical example of recurrent neural networks is what we call word embeddings for language models, and specifically LSTM. And we end up that particular day with a sequence-to-sequence learning. Finally, my last presentation will be cloud computing. I met somebody 2 days ago that was telling me cloud computing has nothing to do with machine learning. I think that's a mistake. We will see when we meet on August 13 whether that is true or not. I can tell you straight away, machine learning has something to do with everything, basically. Everything you can think of. So we're going to look at cloud computing. Now, if you look at the procedure here, deep learning is current and is research-based. Machine learning is generic. if you take the analogy of medical doctors are normally divided into two groups. You have the generalists, which we call family doctors. You go to your family doctor for routine check, you are sick, etc., etc. They refer to them as family doctors or generalists because they have general knowledge in terms of the function of the body, and that is machine learning. Then you have set of medical doctors that we refer to as specialists. These people specialize in different aspects of the body. You have the surgeon, you have the ENT, you have the gynecologist, and so on and so forth. And that is deep learning. Deep learning are specialized. They are not generic. So, what I've done here is to look at the environment, that is Faculty of CIT, look at the graduate setup there, and I chose two examples. Convolutional neural networks. The word convolutional means image processing, sensor, signal, name it, even character recognition. Convolution is used in terms of filtering image, and the filter actually leads to a recognition. So that's why you have convolutional neural network. That part of neural network is specifically developed for that. So that's a specialization. The second one I chose is the recurrent neural networks. It's a feedback type of neural network that work well with what we refer to as word embedding or sentence embedding, and is specifically designed for language processing, natural language. So now, and a typical model that can be used more or less effectively in terms of identifying certain things in natural language is LSTM, is what we call the short memory. Okay, when we get there, I will explain the reason why LSTM is specifically designed for recurrent neural network. And then the last thing is the sequence to sequence, which of course can be used to process any string. Any string, whether it's language or it's not language, doesn't really matter, can be used to process any string. There are other deep learning specialization area that I will talk on August 3. Sorry, this one should be August 3, not August 13, on August 3, okay, just to introduce you. But the most important thing in deep learning is what we are going to do today, is the foundation. If you have that, any other, whatever it is, whether you call it convolutional, you call it recurrent, or word embedding, or sequence to sequence, they are built on top of that foundation. That's all. So today is very important to understand what comes next. Okay? So let's move on now to beginning. Good. Now, it's a little bit of mathematics. I know for some of you it's not new, especially those of you in engineering. Mathematics is a current thing. Those of us from computer science, informatics, and so on and so forth, we may have some difficulty coping with mathematics. But when it comes to machine learning, especially deep learning, you cannot run away from mathematics. It's the basics. What I've done in this presentation is to reduce the mathematics as much as I can without losing the meaning. Okay? So I'll start by explaining simple concept to you about the mathematics we are going to use. Starting from algebra, linear algebra, okay, we talk about vector space. When we talk about vector space, it's simply a set of features within a space. We are no more talking about two-dimensional. We are talking about n-dimensional. And the position of features are referred to as vector positioning. Okay? And the best, the simplest way of representing any information in vector space is making use of matrices. Okay? Matrices. That's all. We use matrices to represent anything in vector space. And it's easy because dealing with mathematics of matrices, you can actually do multiplication, do addition easily, okay? And that brings us to the idea of dot product. When you have two matrices, you can apply dot product. It's a computationally expensive something, but it's easy to handle dot product, okay? Now, when you think about this in a different perspective, you can now map this into a graph. That's why you have neural network. Network is simply a graph. Those of us who have done some aspect of operational research, we talk about developing constraints based on certain objectives. So you develop an equation, this is the objectives, and that objective is only true if a set of constraints are satisfied. And then if you look at those set of constraints, you can simply reduce them to a matrix. And then you can process them easily without any problem. Another thing we are going to use today is aspect of statistics, okay? If you look at this symbol like this, anywhere in statistics, it only means summation, okay? If I introduce an element, I call it xi, I starting from 1 to any level, all I'm saying is that this represents x1 plus x2, and so on and so forth, up to xn. That's all, it's a summation, okay? And we get our average from this by simply dividing by that number, and that's what we call mean. Mean is in statistics, average. Standard deviation is simply how each of these elements deviates from the mean. That's all. That's standard deviation, nothing more than that, okay? Another thing we're going to look at is probability. Probability, it will come on. Before I get to that, one other symbol that is used in statistical theory language is that symbol. If this stands for summation, that is addition, this is simply multiplication. That's all. It represents multiplication, nothing more than that. Okay? So we're also going to use probability because we're going to talk about entropy. Entropy is a probability theory, and if you see a symbol that says probability of certain aspect subject to something, okay? So we want to calculate the probability of A given E. That's simple. That's what it means, okay? So those are some of the symbols that you will see in the slide. So at times in mathematics we use a lot of symbols. And the reason is simple. We want to make life easy for ourselves. So, and that's the reason why you see all these symbols. So don't get put off because you see some of these symbols. They are just simple concepts. You have matrices, you have dot product, you have summation, you have probability theory, and that's all. You'll be able to move on. Okay. One other thing I want to introduce before we go on, the question is, we're going to talk about deep learning. Why are we starting from linear models? Okay? Now, there's a secret here. A secret which I'll give to you. In anything machine learning, the basics of anything machine learning is linear models. Linear. All that machine learning tries to do is to partition either a training set or a testing set into two classes. Class that belong and class that doesn't belong. That's all. No matter how complex it is, or any algorithm you pick up, there is that basic concept. We have two classes, one that belongs, one that doesn't belong. The question is, how do we get to that level? And a basic level is linear module. Linear module leads to what we call logistic regression or linear regression, okay? And that linear regression is actually the father of what we call perceptron. Perceptrons, okay? Now, perceptron is a language that comes from biological process, from biology. You take a tree, it has roots, okay? It has the trunk and it has the leaf. That idea comes from that. And the same thing, you take any living thing, it's a question of perceptron. And perceptron is the grandfather of machine learning. Perceptron is the great grandfather of deep learning. That's all. Nothing more than that. The rest is simple. So what we're going to do right now is to move from linear model, talk about linear regression, talk about logistic regression, move on to perceptron, and once we introduce perceptron, I will try to differentiate between neural network, because perceptron is the simplest neural network. Then we talk about the neural network, and then we differentiate that from support vector machine, and then we move on to feed-forward deep learning. Okay? Any questions so far? I haven't said anything that is complex. I'm just introducing the basic. Okay? So let's move on. It could get tough as we move on, but that's it. So, linear model. Why is linear model? Okay? It is because linear model is the basis for classification. We use it for classifying. And it works naturally with numeric attributes. We'll come back to that later. We need to have that in mind. Linear model works naturally with numeric attributes, and it can be used as a standard technique for numeric predictions. Okay? And it's simply represented making use of a simple linear equation that introduces two things. The first thing is the weight, Wi. Okay? And then the next thing is the feature attribute, AI. So a simple linear model will be x equal to W0, which is the initial weight, generally equated to 1. It's a constant 1. You see, in mathematics, you want to start from a default. So we make W0 1. It can be changed later, but we start from 1. Then the rest, W1, W2, W3, has to ask a value between 0 and 1. The value taken is between 0 and 1. And when you multiply that with the attribute set, A1, A2, A3, you come up with a value for that feature X. And that's a linear model. That's all. And we can take that and rewrite it in this form. Okay? So you look at the summation here. This is what I was talking about. It's the same thing represented, just the summation of the weights and the attribute features. And that is simply a linear model. Okay? That's a linear model. Now, in statistics, that is now referred to as linear regression. Okay? Now, if you look at the definition we gave, it simply introduces you to a single variable linear regression. But that is not useful for anybody. What is useful is multivariable linear regression models. Now, if that is the case, there are two things we need to pay attention to. We need to pay attention to the sign and the magnitude of the weights. The sign is simple, it's either negative or positive. That's all. Now remember, we are talking about vector space. A negative weight moves the linear line away. A positive weight either maintain the linear or push it positively towards a different direction. And then the magnitude is actually the positioning in vector space. So if we are giving an example like this, which is a simple example that talks about office renter module that consists of 3 descriptive features: the size, the floor, and the Wi-Fi broadband size. Okay? Now, when we look at this, we are given the weight. The weight for the size is 0.6270. That of the floor is negative weight, and that of the broadband rate is a positive weight, but it's smaller. Now, the idea in linear model is that looking at the weight, you should be able to determine how each feature contributes to the objective function. For example, if I want to rent an office space, the question is, what is important? What contributes to the cost of renting? Okay? Looking at this weight, if we want to believe, just base our analysis on the weight, we can see that the size has a better weight compared to the other two, to the floor and to the broadband rate. We can conclude here and say, okay, the size contributes more to the amount of money you are going to pay to rent an office space compared to the floor or the broadband rate. Now, in this example, it works fine because the weight actually works fine. But in majority of examples, when we are talking of big data, you cannot do that because the weight may not show a significant information for you to be able to decide that, okay, this is the only thing that contributes to the objective function. Now, what can we do? We can move on by calculating the standard error, using that standard error to calculate the t-statistics, and from the t-statistics, we can pick up the p-value, and the p-value, look, when you get the slide, the grammar for all this is there, so look. And calculating the standard error is simply, okay, taking the summation of all the features divided by the population size minus 2, okay, and then having a standard error for the overall model. Use that standard error for the overall model to calculate standard error for each descriptive feature. And from there, you can calculate the t-statistic. Now, I'm showing you all this equation. You don't have to do it. Actually, using the tool, all this will be calculated for you automatically, right? But you need to know what led to, why are we going to actually make use of t-statistics? Because t-statistics is based on two things. It's based on the standard error for the descriptive feature as well as the weight of that feature. Remember, if we go back to the table, we talk about the weight. So the standard error and the t-statistics is calculated based on the standard error for that feature as well as the contribution of the weight. Okay? As well as the contribution of the weight. And that is important. We are not just looking at just the weight, we are looking at the quality of the weight. That is, if that weight is calculated compared to other descriptive feature, what makes it better than the other feature? That's what standard error means. Okay? Another way to look at it is, what is the performance, accuracy of that weight? That's another way to look at it. So in this case, I can simply say that the accuracy of this weight is roughly around 95% based on the weight. So we use those two quantities to calculate the t-statistics. And picking the p from the t-statistic, we can now say, okay, we set our p-value, which is a threshold that says that for a p-value that is less than the required significance level, typically is 0.05, sorry, it should be 0.05, we can reject the null hypothesis. In other words, if the accuracy of the weight is less than 95%, then reject that particular, I could not, the null hypothesis, okay? So if we come back to the table here, we look at this. This p-value is less than 0.05. So it confirms what we knew from the beginning, that size contributed more to the price of office rental compared to floor or broadband rates. Because this also gave us, based on that threshold that says that 0.05, this is less than that, so we can conclude that size contributes more. Now, if we look at these two, we can see that these actually, they are not less, okay? And in that case, we can accept the null hypothesis in these two cases but reject the null hypothesis for this one. Now, the problem here is this. If we want to use this in machine learning, it's a lot of work. Calculating the standard error, calculating the statistics, finding the p-values, setting the something, it's going to be a lot of work. So instead of that, we can actually do better. Instead of going back to do the standard error, do the t-statistic, look for the p-value, we can make use of what we call the squared error. And the squared error is basically based on the feature itself and the summation of the Millian module for the feature, which is the weight multiplied by the attributes of the feature. And it's called square error because it's squared. Now, this will give us information on the accuracy of that particular feature vis-a-vis whether it belongs to the correct class or it belongs to the opposite class. Okay? And this is what is generally used most of the time. The square error is used. Now, the problem here is that oftentimes you want to do better than that, and you want to get to as far as possible to what we refer to as absolute error. But that is not always feasible. Because what you want to do in classification is chosen in terms of prediction by error. The less the error, the better the prediction. So what you want to do is to minimize the absolute error. And if you can minimize the absolute error, you know that whatever you predicted for a feature, whatever class that feature belongs to, is correct. Correct and true. Cool. Okay? So we want to get as far as minimizing the absolute error, but that is difficult. We can be contented with the square error. We'll come back to error in a few minutes. Okay? So now, with this foundation, we can talk about classification now. The general statement is any regression technique can be used for classification. And we have two things. The first thing is the training. And the second aspect is the prediction. What are we doing with the training? Performing the training is performing a regression for each class. And the general notion is, sorry. The general notion in terms of boundary is 0, 1 boundary. 0, 1 boundary. Okay? Now, why 0, 1 boundary? Those of us who are conversant with machine learning or with neural network in general, the simplest neural network is what we call a binary feed-forward neural network. It's the simplest. And it's also called 0, 1. Because two things. The entropy function behaves as a 0, 1. The activation function behaves as a 0, 1. And the 0, 1 comes from the fact that 1 represents the target class. 0 represents the non-target class. In other words, I have a training set. I'm trying to look at each of the pieces in the training set, and I'm trying to determine which one of them belongs to the target class, and that's my 1, and which one of them is outside of the target class, and that is my 0. Two problems here to start with. Number one problem, not all training set or simulation module can be bounded between 0 and 1. It's a restricted boundary. And this means that anything that is outside of 0 and 1 cannot be handled. That's number one problem. Number two problem is that if anything falls between 0 and 1, that is, it's not 0, it's not 1, how do you interpret that? How do you interpret it? Because the binary says if it is 1, I know it belongs to the target class. If it is 0, it doesn't belong to the target class. Now, if the value is 0.4, where does it belong to? If it is 0.7, where does it belong to? So this theory, regression approach, doesn't allow us to do that. So those are the two main problems. To solve the first problem, that is the membership problem, then what is applied in statistics, because the whole idea came from statistics, is to apply what we call logistic regression. Okay? Logistic regression, we'll come back to that. But I want to address a different problem before we get to statistic logistic function. Okay? The other mini problem that falls within that is that we said at the beginning, if you remember, let me go back to my first slide. We said, work most naturally with numeric attributes. And it's a standard technique for numeric prediction. Okay? Now, if your attribute is not numeric, what happens? That's another question that we need to answer. And there's a simple solution to this. Okay? Assuming we are given a feature that we call energy rating. Remember in our example, we look at the size, the floor, the broadband rate. Now let's add another feature to that, energy rating. And that energy rating came with a description. It says there's energy rating A, energy rating B, and energy rating C. Those are not numeric. And remember, our linear module logistic regression, linear regression can only undo numeric. Okay? So the simple thing we do is to convert those non-numeric into numeric. So instead of having one feature now that says energy rating, we introduce 3 different features to replace that. Energy rating A, energy rating B, energy rating C. Okay? And where energy rating A applies, we use a 1. And where it doesn't apply, we use a 0. Are you getting the point? Remember, the boundary is 0, 1. Okay? So that works. Now, there's another problem with that. Not all features that are non-numeric can actually be categorized as a 0, 1. But it's a simple solution which works perfectly well in terms of features that are not numeric. Okay? So now that we have that, we can actually, and what is a regression? If I want to calculate my rental price, I pick up my objective function will be the weight 0. Remember I told you initially it's 1. 1 plus weight 1 multiplied by size plus weight 2 multiplied by floor. Now, because I've introduced 3 features, now to replace one feature, I have to treat them individually, separately. Weight 4 multiplied by energy rating. If this is 0, the result here will be 0. If it is 1, it multiplies by the weight, and so on and so forth. And that will be my objective function for renting a space in the office mall. Are you following the argument? I'm doing this in order for you to that when we get to more complex things, it makes sense. Okay? So now we more or less have a solution for a non-numeric attribute. Okay? By replacing it with something else which we can make numeric. But it doesn't solve our problem of the boundary. Okay? In order to solve the problem of the boundary, the statistician, they came up with what we call a logistic function. And what does that do? Remember, our previous linear module is simply W0 plus W1, weight 1 multiplied by A1 plus and so on and so forth. Now, logistic regression replaces that target, okay, the target, and if you remember W0, the weight 1, the weight 0 is 1, okay, it's 1. We now put in a probability of that weight being 1 if all these are true. And instead of that, logistic now replaces it with a log probability. And that log probability now, we can transform what originally was a linear boundary 0, 1 to a linear minus infinity to plus infinity. Which means now we are no more constrained by that boundary. We can now get out of it and deal with a bigger problem. And when you apply logistic function, I'll come back to that, this is what it does. It transforms what you have into a representation such as this. And two problems are solved here. Number one problem is that the boundary now is no more, from to plus infinity, it's no more 0, 1, it's from minus infinity to plus infinity. Number two problem, interpreting a 0.4 is also possible. Okay? If I pick a 0.4, I can map it to something here. Whatever I got there, depending on the entropy function and the activation function, I should be able to determine whether it's close enough to the boundary so that I can translate it as the target class or outside of the target class. Okay? Now, for the sake of those of us that are not too mathematically inclined, the question is, what is logistic function? That's the function. It's a simple function. It's 1 divided by 1 plus what we refer to as Euler's number, which is exponential raised to the power minus x. So you pick up an attribute, you pick up a feature, you can calculate the logistic function for that, simply like that. And when you apply it, okay, we apply it back to our previous equation, we simply replace our x with the weight and the attribute. Here I'm using b here, okay? Pardon me for that. I have a different set of slides. So this is simply our A, performer A1, A2, A something there, and that's the weight. And we just translate it to that. That's all. And we calculate that. And we get a nice thing that comes out, which is no more a boundary of 0, 1, is now minus infinity to plus infinity. So we are free now from the restriction of linear module. When we apply logistic function, then we move from linear module to logistic regression. Are you following the mathematics? We are still far away from deep learning. We are just moving little by little, okay? So we have that, okay? So, and for example, if I now change my weight 0, remember I started by saying my weight, I assume that my weight 0 is 1. Now, with the logistic regression now, because I'm no more bounded by that boundary, my weight can be anything. It can be anything, provided it's working fine for me. So I can now put my weight, for example here, if I make my weight 0 to be 1.25, and my weight 1 to be 0.5, and I plug it into that equation for the logistic regression, I come up with a graph that is similar to that. But then within this graph, let's assume here we are talking about office space rental, and we are looking at just the size, the floor size only. So my weight 0 is a constant, which is 1.25. The weight attached to my size is 0.5. Okay? So I can read off this graph and determine how much will I pay easily. That's what machine learning does. It generates an objective function with a set of constraints. And if those constraints are satisfied, then it produces a solution for you. So any machine learning, that's what happens. It produces, and you can now come up with a prediction of what is it, okay? And you see, there's one thing in mathematical science, we don't talk about exact solution. We use jargon such as maximum likelihood. The reason for this is that everything is based on probability theory. The closer it is to 1, the better it is. That's what we call a maximum likelihood. The farther away from 1 it is, the less important it is. Okay? So you see sort of that jargon, maximum likelihood. Okay? And then other jargon that you see is that you want to maximize something or you want to minimize something. For example, error, we want to minimize error to have a good prediction. And we want to maximize the performance also to have a good prediction. So those are the jargon technical jargon that is generally used, because it's basically within probability theory that says that everything that gets close to 1 is better, is the best. Okay? So you have something like that is that. Okay? So now we've solved the problem of the boundary. Okay? We solved the problem of the boundary. But still, solving that problem introduces some level of complexity into our system. Now, our calculation becomes more complex. And in order to reduce the complexity, we now introduce the idea of maximizing the probability of the observed trading such that we now go into log form, likelihood. Okay? Now, the beauty things about logarithm is that you can, remember, we've opened our boundary to minus and plus infinity, would give us the access to do anything we want to do. But for us to actually do good prediction, after having that, we still have to come back to our 0, 1, one way or the other. And the only way to come back to that is that now we can make use of logarithm. And what logarithm does for us is now to take what seemingly to be complex back into the same boundary that we can easily prove. I'll give you an example. In character recognition, assuming I want to recognize the digit 7. Okay? Digit 7. Now, in the machine, that is in terms of digital representation, how is this represented? Representation that machine will see is 0 to 255. So, okay? That is 256. And that is 2 raised to power what? For those of us who still remember our architecture class. Okay, don't worry. Now, let's go back. 0 represents white space. Purely white space. It's like you go to your doctor, you just done an X-ray or MRI or whatever it is, or CAT scan, and then they produce that film. And generally when you go to your doctor, they put it under the light to be able to read it, right? It's the same thing with digital representation. It's like projecting light into something and trying to read. All the white spaces are represented as 0. Now, starting from the gray to black, represented from 1 to 55. 255 gives you pure black. Are you getting my point now? Something like 105 will give you something grayish. Okay? So, it's just how that thing is focused. So, that's what digital representation appear. So all these spots in this character will be 255. Each of these lines here will be 255. Outside of it will be 0 to whatever, depending. So now remember we said we now have minus infinity to plus infinity, but for machine to process it, we still have to come back to that, right? So what do we do here? We divide everything we capture by 255. Everything we capture by 255. So divide 0 by 255 is still 0. And the maximum you can have is 255. Divided by 255 is 1. So we've brought it back to 0, 1 so that the machine can process it. What we did before to get out of this boundary is for modeling purposes. But for the processing, machine processing, it still have to come back to 0, 1. Up to today, nobody has produced a processor that can process anything other than 0, 1. If you have one, let me know. I'm talking about machine level learning here. I'm not talking about programming. Machine level, still 0, 1. And you have to be able to get that representation actually to do some prediction. So that's what we have. So in order for us to be able to do that, we now introduce log into the computation. And what log will do for us is actually to be able to now bring us back to either 0 or 1. But not only that, we can also interpret whatever is in between. Not like before where it's either 0 or 1, but now we can interpret 0.4, 0.5, 0.6, and so on and so forth. We can interpret it. Okay? Are we still following? Great. Look, I'm trying to make it easy as much as possible. So now, the question is, how do we maximize this log likelihood? It's simple. We make use of what we call the weighted least square in terms of optimization. Okay? I won't go into the mathematics of that, but that's what is known normally. Now, the next question we want to answer is that now we've dealt with logistic regression when we have only two classes. Two classes. If it is 1, it belongs to the target class. If it is 0, it belongs to the outside of the target class. The question is, life problem is not always divided into two classes. Life problem is not a question of white and black. In between white and black, you have so many other shades of life problem. And therefore, we get to multiple classes. So what do we do when we have multiple classes? It's simple. We can do logistic regression for individual class, and at the end of the day, we now combine them together. Now the problem with that is that it may not add up to 1. It may not add up to 1. It can be less than 1, it can be greater than 1. In most cases, it's greater than 1. Okay? So, how do we solve that? We can apply what we call pairwise classification. And pairwise classification is simply taking two classes at a time. So if I have 7 classes, processing that is 7 factorial. Are you getting my point now? I take class 1, class 2, class 1, class 3, class 1, class 4, class 1, class 5. Then I drop class 1, take class 2, class 3, and so on and so forth. That's it. Now, doing that, there's a problem. You have k into k minus 1 divided by 2 classification module. That is, you have a lot of modules. Well, it's a problem mathematically, but remember, we are talking here about the data, the training data, as well as the testing data. We can do something to the training data such that we don't have to use all the training data all the time, so we can reduce the complexity. Okay? So if we assume that the data is evenly distributed to n over k instances per line, then we reduce it substantially. Remember, when we start, we pick class 1, class 2. So we are only treating data related to those two classes. We're not looking at the other. And when we move on, we have class 1, class 3. We're only looking at class 1, class 3 data, and so on and so forth. So this explosion is actually theoretical. It's not the case, because when you look at the data size actually reduces based on the pairwise. So that algorithm worked very well. And it worked, and it actually, at runtime, we can be proving that the solution becomes linear. K minus 1 into n. That's all. If we still remember our calculus, k minus 1 divided by n is what? So if I have 7, I'm picking pairwise, that will give me 2 over 7 factorial, which means in that case my k is 2 and my n is 7. So that's what I have here. So if I'm picking 2, this is 2 minus 1 into n. It's simply n. It's 7. That's it. Okay? So, and that's that. I don't want to go into any mathematics here, but that's what you have there. Pairwise classification does that. Okay. Now that we know, I assume we know everything about linear model. The next question is, how does machine learning actually make use of this logistic regression to do what it's doing? It's simple. I will show you a simple graph. Assuming I have, this is my scatter something. I will do something here. Okay, need another color. So what logistic or linear model in general does is to generate an equation that determines what we call the hyperplane. And the hyperplane separates the target class from the non-target class. That's all. In other words, my plus here represented those data point or attribute that belongs to the target class. And this represents those that doesn't belong to the target class. An example, we are looking for a marker that determines a particular cancer, let's say prostate cancer. So you collect different markers. The medical doctors, they know those markers when they see it. But we want to be able to use a machine learning to predict whether an individual is susceptible to have prostate cancer or not, depending on the marker gathered. So when you gather the markers are your data. Okay? And you use that data to train. When gathering it, you don't know whether the marker belong to the target class or not. So you use it to train your machine. So those markers that are positive for prostate cancer will be put in the target class. Those markers that are not positive to prostate cancer will be put into the non-target class. Okay? Now the problem now comes with markers that are on the boundary. They are close enough to the plane. They cannot be interpreted to be the target class or outside of the target class. And that's the function of the hyperplane. The hyperplane, number one, separate the classes. Number two, look at those points that are close to the hyperplane and try to make a prediction as to whether they belong to the target class or outside of the target class. Another example, you are dealing with language processing, okay? Translating from English to French, okay? Now, in English, we talk about the red car, right? So the adjective is before, the red car. In French, is la voiture rouge. Voiture means car. So translation in French is actually the car that is red. That's translation in French. So if we are using positioning, in English, you will come across red before car. In French, is car before red. Are you getting my point now? The question is, you are translating from one to the other one. You have two words that are different position, and they will be positioned in the hyperplane differently. How do you bring them together to say that they mean the same thing? So that's the function of the hyperplane. It's what we call the objective function, the hyperplane. It's where that constraint is equal to 0. Okay? The closer the point is to 0, the more difficult it is to determine where does it belong. Okay? So, and that's what you are. An hyperplane is what is used a lot. Now, be careful. We are limited as human beings to two-dimensional space. Okay? Now, all these things that I drew, they are not exactly this way in vector space. Vector space is a multi-dimensional space. They are all over the place. Okay? So the hyperplane is not just a single line, it's like a ring. Okay? It's a plane, that's why we call it a plane, that's why we don't call it a line. So it's a ring. So there is, and you look at it, that's number one. Number two, here we are talking about two classes. Imagine having multi-class problem, which means you have a lot of hyperplane all over the place. Okay? And dealing with that is actually where linear models come out very good. Logistic regression come out very good. Okay? So we move from there. I'm trying to do this, I will have read the mathematics for you and move ahead, but it may not make sense to some. So now what we are now saying, remember, our logistic function is 1 over 1 plus exponential into this. Look at this on the right hand side. What do you have there? That's our logistic function. Okay? Now, the decision boundary in the case of two classes is where the probability of this logistic function equal to 0.5. It's where it equal to 0.5. And this happens when this is 0. And remember, this is what you use in determining whether a point belongs to the target class or not. That's what you use there. Okay? So now, interpolating that, looking at the two classes, okay, in terms of hyperplane, when class 1 is greater than class 2, okay, in terms of hyperplane, in terms of that function, then it's interpreted to be in the target class. When this happens, it's interpreted to be out of the target class. Okay? The question then is, what happens in between? What happens in between then introduces us to a different, all other things that comes into dealing with linear modeling in terms of the output. The output we get from linear modeling now can be passed to another function so that we can interpret it correctly. Okay? And this leads us to the idea of the perceptron. Okay? It leads us to the idea of the perceptron. And it's simple. If the weighted sum is greater than 0, we predict the first class, otherwise the second class. And that's the whole idea of perceptron. Okay? And perceptron algorithm is very simple. This is what I put there. You set all the weights initially to 0. Set it to 0. Now you pick up the instances. You pick up an instance, okay, in the training data. If that instance is classified incorrectly, you see, the way things work in algorithm and mathematically is that you have an assumption at the beginning. You could be right, you could be wrong. Okay? You have an assumption at the beginning, you check that assumption. Okay? If it is classified incorrectly by the perceptron, then if it belongs to first class, add it to the weight vector. Else, subtract it from the weight vector. That's all. It's simple. I pick an instance, I assume that it's classifying correctly. If that is the case, I check it with the weight in terms of it belongs to the first class. If the assumption is that it belongs to the first class, I add the weight to it. Okay? And I send it back to the perceptron. If not, I subtract the weight from it and I send it back to the perceptron. And you do that iteratively. Eventually, the correct classification will come in place. Eventually. How long? I don't know. It depends on the size of the data. It continues until it gets to a level where you can say, okay, this is good enough. Okay? So, and it's not only perceptron that does that. We have other functions, but first of all, let's limit ourselves to perceptron. Now, perceptron is a neural network. Why? Because the input layer consists of W0, which we refer to as bias, attribute multiplied by weight, attribute multiplied by weight. It goes on into the middle layer where the computation is done, and then you have the output. Okay? So that's the simplest neural network. Okay? Another function that can be used other than perceptor for linear module is called the willow. It's close to linear module, and willow is based on mistake-driven algorithm. The idea is there's a mistake from the beginning, then you try to correct that mistake, and then you move on. And it applies multiplicative process instead of additive process. So if you look at this algorithm, it's similar to that of perceptron, but it's different in the sense that instead of additive process, it's a multiplication process. That's all. And it's based on the perspective that there's a mistake from the beginning, and then we want to correct that mistake, and then we multiply by a constant, which we refer to as alpha. Okay? And if we multiply by a constant, if the result is 0, we leave the weight as unchanged, and then we go on. If the result is different from 0, then we modify the weight and then move on in the process. Now, another algorithm that can be used is called balanced willow, which of course we can use 2 weight factors instead of 1 weight, and in that case we have different weight for each class. In the pairwise approach, this algorithm works very well because you have 2 different weight sets, weight factors. You use one for one class, you use the other for the other class. Eventually, you get to a level whereby the instance is classified correctly based on this equation. Okay. So far, so good. There are 2 things I want to introduce before we go on to feed forward the network. Number 1 is the distance. In machine learning, distance is very important. But when we talk about distance, it's not a linear distance, it's a vector space distance. Those of you who attended my first presentation on machine learning, I presented a number of distance. One of them is what we call the Euclidean distance. It's Euclidean distance. Okay? Euclidean distance is a vector distance that gives you the notion of distance. For example, if I want to calculate the distance for 2 colors, blue and yellow, okay? Positioning, vector positioning is used, or don't let's make it complex, let's make it simple. What's the distance between A and B? Digit A and letter B. That's what we're talking about here. So in vector space, that is possible. Linearly, it's impossible. Okay? So we can use Euclidean distance, and Euclidean distance is simple computation, which is represented as we have it there. And there are other type of distance that we can use. Remember, we talked about city block metric, which is based on the notion of Manhattan distance. For those of us who attended the first one, we talked about Manhattan distance. What is the whole idea? In Manhattan, in New York, if you go to that neighborhood, nearly all the street is one way. Nearly all the street in that neighborhood is one way. And the reason is simple. When they used to be dual way, you have a lot of traffic congestion because it's a densely populated neighborhood, and people coming from out of town going to work pass through that neighborhood. Everybody, everything goes through that neighborhood. So there was a lot of congestion, okay? And one of a scientist, statistical theory lining scientist, devised the distance such that it can be applied, that is, make majority of the road to be one way. If you're on this road, you know there's no other car coming this way. You're just going one way, okay? So, and that actually reduced the congestion by almost 70%. 70%, by turning nearly everything to one way. And the notion is simple. I have something like this. Okay? This is my Euclidean distance. That's my Euclidean distance. My city block metric, which is Manhattan distance, is this. Plus that. That's simple. Because everything is one way. So there's no way you can actually move from here to here. You have to go around. Okay? So, and there are so many other distances that are based on index, vector index, and cosine distance, and so on and so forth. But the most popular that is used a lot in machine learning is Euclidean distance. Okay? So that, we'll come back to that again in a few minutes. Another thing that is used a lot in machine learning is normalization. Remember the problem of converting a non-numeric attribute feature to numeric? That's one. Another thing is converting, you know what we did here? Converting 0 to 255 divided by 255. That's another one. So it's generally called normalization. Generally called normalization. And normalization is applied a lot. And it's good because when you have missing values, normalization can reduce the effect of missing value on your data. Because missing value can cause a lot of problem in prediction. And you want to be able to mitigate that, reduce it to the minimum, so you apply normalization to it. That's another language that we need to learn. Okay. Now, the last thing we're going to talk about before we go on to feed forward is support vector machine. It's a typical logistic regression, which is a little bit different from neural networks. A little bit different from neural networks. Okay? In neural network, remember, the hyperplane is simply that line. In support vector machine, hyperplane is a boundary. It's not just that line. It's a region. That's what separates support vector from neural networks. That's all. So that's why I want to introduce it, because often in deep learning, we don't hear about support vector machine. We talk about neural network, which is good, okay? But there's support vector machine, and this is very new. It came out through a research in 1999, research conducted in statistical theory learning, the notion of logistic regression, how you can extend it to make it perform better. Then they came up with support vector machine. Actually, the implementation is called support vector regression. That's the original name, support vector regression. Okay? And the idea is simple. Generally, in neural network, this is our hyperplane. The initial weight plus the sum of all the weights and the attribute features. That's how we get our hyperplane. Support vector introduces another thing that says that greater than 0, that is above, and that less than 0, below. There's a boundary there that when you have points that belong to that boundary, you need to be able to maximize it in such a way that you can do correct prediction. In other words, mathematically, neural networks is based on what we call empirical evaluation, while support vector machine is based on structural evaluation. Okay? So, and that's what you have, that's what separates support vector machine from neural network. Now, since 2002 or 2003, the notion of structural computation has been introduced into neural network, and that is what we call weight decay. Okay? I'm going to talk about that in my cloud computing later, not today. So I need to present this so that we can, when we are reading papers, we are reading something on machine learning, and we come across support vector machine, we see that it stands alone compared to the rest. The reason for that is because of the way it's constructed, that says that it's not just the question of the hyperplane alone, it's also the boundary between them. And what he tried to do is actually to maximize that boundary such that you can have a good prediction. If you compare these two, they are the same sets. Here, the boundary is in form of, could be the first predictive boundary for the support vector. And then in trying to maximize that boundary, okay, in order to satisfy that constraint, you then get to that point. And when you look at it, you have 1, 2, 3 that fall on the boundary. And now, assuming you want to write query for this and this, you have two data points that you want to write query for. You want to determine what class they belong to. What happened here is that support vector machine will use the information about the boundary in terms of this and that to be able to determine if this belong here or belong there. Which of course is a little bit better than what neural network does. Neural network simply look at the Euclidean distance only. But support vector machine look at what we call Euclidean norm. It's also based on Euclidean distance. Okay? And Euclidean norm is what? We calculate the distance. Euclidean norm is calculated as this. And then you now make your decision based on that boundary. And what does that boundary? Let me try and get a color here. If I can. Okay. Now, the boundary we are talking about is this. That. Okay. And here also. Close boundary. Okay? You see, that boundary is simply 1 over Euclidean norm. That's the distance. From the hyperplane to that boundary is 1 over Euclidean norm. And because we have two of them, one on this side, one on that side, and we can prove that they are equal, therefore the size is, because they are symmetrical, is 2 over Euclidean norm. So what support vector machine try to do is now to maximize that quantity. Maximize it. In other words, when you generate the first prediction, you have that boundary. You now pick up that quantity, 2 over Euclidean norm, and try to maximize it based on the objective function, increase it as much as possible to the limit. Okay? In other words, get more points onto that boundary compared to the previous one. If you look at this, you have only 2 points. Increase, maximizing it, bring it to 3 points. So the more points you have on that boundary, the more accurate the prediction is likely to be. That's what support vector machine does. Okay? It uses that, maximize 2 over Euclidean norm, subject to that constraint. So the objective function here is A, subject to that. Okay? Now, the problem is that when that is done, it generates a computation that is based on dot product. Dot product is computationally expensive because you need to be able to linearly separate the elements, okay? But there's a solution to that. The solution is simple. We apply what we call the kernel. That's where the kernel comes. So when you look at machine learning algorithm, we talk about kernel this, kernel that. The simple idea is this: we have dot product because we are dealing with matrices, we are dealing with vector mathematics, which are computationally expensive. So if we replace them with kernel, we can reduce the computational cost. That's all. And we have different types of kernel. You have linear kernel, which is based on that. You have polynomial kernel. You have the Gaussian radial basis kernel. You have soft. There are so many of them, okay, that can be used, okay, depending on the problem you are trying to solve. Now, the moment you move away from linear to polynomial and moving out of polynomial, it becomes very complex. Why? There's that activation function that needs to be determined. And that activation function actually determines not only the accuracy, but the time you spend in the computation. Okay? So, and that's the whole idea about support vector machine. So if you miss everything, just have this in mind. The whole idea, starting from linear module, we want to be able to get ourselves out of the boundary of 0, 1 in terms of modeling. We introduce logistic regression to do that, so it free us from the boundary so that we can model any problem. And then, moving from logistic regression, in order to do machine processing, we need to come back to a 0, 1, and therefore we apply probability logarithm in order to do that, so that we can come back to what the machine can process. And then from there, we need to be able to address more than one class, okay? Moving on from linear that address 2 classes into multi-regression model. In that case, we now introduce a pairwise approach to be able to evaluate it. And then that leads us to perceptron, and that leads us to neural network. That's what we talked about. And we move on to differentiate the classical neural network from support vector machine. Okay? And I told you that the idea of weight decay has already been introduced into neural network. It's the same thing that is used in support vector machine. So we have now a set of neural network that we can use. Any questions so far? I've been doing all the talking. How many people enjoy the mathematics? You see, the whole idea is this. You see, anything you are going to do, there's something we talk about, especially in Africa. It's more or less like an adage or a proverb. Now, if you want to help somebody, you don't just show up every morning and give that person a plate of food. It's good. You are giving the person a plate of food, right? But if you really want to help the person, why don't you take that person to the farm and show him or her how to farm? That's it. You are helping that person more than just showing up, giving a cup of coffee and all this. Let that person be able to actually make the cup of coffee by himself. And that's the whole idea. You want to use something, you need to know the reason why that thing is that way. So that later on, if you encounter a different problem from what you are used to, then you can actually be able to sit down and solve the problem. That's the whole thing, okay? It's not about trying to teach you mathematics or what it doesn't, okay? So now let's talk about feed-forward neural nets.
5 minutes break, is it possible?
Yes? Yes.
Can we ask for 5 minutes break?
Good. I think I should be the one tired. Yes, we can go for 5 minutes break. No problem. Please don't make it more than 5 minutes. I want to be able to finish slowly.